Sound. What is sound? Sound is a vibration that is transmitted in a medium, can be heard by a human ear. Human ear cannot hear below 20 Hz and frequencies below this are called infrasounds. We cannot also hear frequencies that is above 20,000 Hz and these frequencies is known as ultrasound. Next is ultrasound. Ultrasound is a sound have a frequency greater than 20,000 Hz cycles per second. That is sound above the audible range. Frequencies in the range of millions of cycles per second are used for medical diagnostic purposes. Now we will move to the advantages and disadvantages of ultrasound. Firstly, it can be directed in a beam. Secondly, the energy is reflected off of small objects. Thirdly, it obeys the laws of reflection and refraction. Lastly, it brings no injuries to health. Here are some disadvantages of ultrasound. The energy propagates poorly through a gaseous medium. Ultrasound transducers must have airless contact with the body during examinations. Ultrasound images are relatively noisy and have poorer contrast than X-ray and MR modalities. Acoustic waves. Organized vibrations of the molecules of a medium that is able to support the propagation of these waves. Vibrations are organized in a sinusoidal fashion. Sinusoidal sound wave. What it is? It is a series of areas of compression and rarefactions. Sine wave with the peak representing the pressure maximum and the nadir representing the pressure minimum. It is a combination of one compression and one rarefaction, represents one cycle. Its distance between the peak of one compression to the peak of the next is a wavelength. Here you go. There are some formulas for you. The first formula is for wavelength, secondly for velocity, thirdly for phase velocity, fourthly for speed of sound in a medium, and lastly for impedance. All of these formulas definitions can be referred to the earlier notes given. The use of ultrasound as a medical imaging modality became a practical with the development of small piezoelectric crystal transducers. You can refer this diagram for more information. As the crystal expands and contracts, it produces compressions and rarefactions and corresponding sound waves. Effect of high-frequency sinusoidal electrical stimulation. Firstly, on piezoelectric crystal causing the crystal to vibrate. Next, it produces a sinusoidal vibration. And lastly, it sent through the conductive medium, human tissue.
Next, I am going to explain about receiving ultrasound. Another property of piezoelectric crystals, or PEC, is that it's able to receive the ultrasound wave. This is because when the crystals being compressed by the reading ultrasound, it will produce voltage, and this voltage will be used to measure the intensity of the returning sound wave. In typical ultrasound machine, it will both transmit and receive the ultrasound by utilize properties of the PEC. Thus, it's able to listen to the ultrasound. I am going to explain how the ultrasound machine works. There are several steps and I am going to explain using this figure. Firstly, on the left figure, the machine will switch with the voltage source to expand the PEC, thus transmit the ultrasound wave to the object. Next, it will quickly change its connection to the meter, and the returning sound wave will compress the PEC, thus the voltage will go across A and the meter will read the voltage. This process will repeat it rapidly, and all of the information then will be processed and translated by the computer that was attached with the machine. There are also probes that will be connected to the machine. This is the inside figure of the probe. As you can see over here, there are several PEC instead of one in the probe, and there are also acoustic lens and so on. This is also the working principle of ultrasound machine. Next, I'm going to explain about precaution when utilizing ultrasound properties. There are two precautions in order to utilize the properties of ultrasound, which are the presence of air and using liquid. When using ultrasound machine, it is very important to eliminate the presence of air between the probe and the tissue. Why, you may ask? It is because the smallest presence of air will cause the ultrasound to be reflected away instead of penetrating the skin, thus cause the reading and the image to be blurry and indecent. The other one is ultrasound wave is able to transfer in liquid easily. Due to this characteristic, typically there will be a thick liquid or jelly that will be used to intermediate the skin and the probe. The jelly will help to eliminate any air bubbles present and provide an easy pathway for the ultrasound to traverse. As you can see on the figure of the left, it shows the air reflected the ultrasound wave, and the figure on the right shows how jelly eliminate the air bubble, thus create an easier pathway for the ultrasound to penetrate the skin. Next, I am going to explain about what happens to ultrasound wave when it enters our body. As an overview, the ultrasound wave that enters the body will have two results, which are some will return back to the probe to give information for the machine to produce image. The rest will be absorbed by the body, thus cause it to be lost. Those results is the cause by the process the ultrasound wave undergoes, which are attenuation, reflection, and refraction. I am going to explain about attenuation, while the other two will be explained by my other member. Attenuation can be defined as loss of energy as an energy travels across medium. This loss of energy can be measured or expressed through the changes of intensity of the ultrasound wave. Ultrasound intensity is measured in watts per square centimeter. The difference between the ultrasound wave is expressed as decibels. An attenuation coefficient is the rate of attenuation, which means that the higher the coefficient, the image will become more unclear. For soft tissues, the attenuation coefficient is half frequency per centimeter. Attenuation of ultrasound wave in body is a phenomenon where the wave is when the body absorbs the ultrasound energy, thus cause the wave to disappear. This wave did not return to the probe and therefore categorized as wasted. The ultrasound wave will undergo more attenuation as it need to pass through more body tissues. This is one of the major reasons that the difficulties of getting deeper structure image is higher than those tissues nearby the skin surface. As you can see in the figure, in the most left one, with the mild figure or the mild images, it has attenuation coefficient of 0.67 decibel, the lowest compared to the these three. And the most right one, it has the highest attenuation, which is 0.94 decibels. If you compare both of these pictures, you can clearly see the one with the higher attenuation coefficient has an more indecent image and much more blurrier compared to the other one.
So I want to continue in this topic about refraction and reflection. So first we go through refraction. Okay, refraction occurs when the ultrasound signal is deflected from a straight path and the angle of deflection is away from the transducer. Ultrasound wave only refracted at a different medium interface of different acoustic impedance. The angle of refraction is dependent on two things. First, the angle of the sound wave strikes the boundary between the two tissues. Second, the difference in their propagation velocities. So, for the second point, we can see through the this diagram, if the propagation velocity is greater in the first medium, refraction occurs toward the perpendicular A. And if the velocity is greater in the second medium, refraction occurs away from the originating beam, which is B. Okay, why sound is not reflected back to the transducer? Why? Okay, it is because it may cause the image being depicted may not be clear or potentially altered. Okay, next is reflection. Reflection is refers to the return of the sound wave energy back to the transducer. It allows the image to be generated by the ultrasound machine. As the ultrasound wave crosses from one tissue to another, each with different acoustic impedance, some of the wave is reflected back at each crossing. The blue arrows, we can see the blue arrows? It reflected back at each crossing. Then, multiple reflected wave return to the probe, and the machine uses this information to display an image showing different tissues. Then, irregular surface objects, such as nerve scatter, the ultrasound wave in all directions. A small portion of wave are reflected back to the probe, the blue arrows, and it may cause scattered reflection. And then, if an object is large and smooth, like a nerve-blocking needle, all the ultrasound wave will be reflected back. It may help us to clearly see the needles when performing ultrasound-guided nerve blocks. Waves are reflected back in one direction, and this we can call as specular reflection. Next, there are two types of reflector, which are specular reflector and diffuse reflector. Specular reflector, the wavelength is smaller than the boundary. Diffuse reflector, the wavelength is larger than boundary. Specular reflector is on flat surface and diffuse no flat surface. As we know, diffuse reflector will produce scattered reflection. Then, the percentage of beam reflected at tissue interfaces depends on two things. First, tissue's acoustic impedance. Second, beam's angle of incidence.
Amplitude mode. Amplitude mode is the simplest form of ultrasound and not frequently used. The function of amplitude mode is to measure length. For example, ophthalmology use it to measure the diameter of the eyeball. Imagine that the red circle is the eyeball and the pink arrow is the diameter. So how is the amplitude mode works? From the picture given, the black screen is where the amplitude will appear, and then the arrow is where the ultrasound waves is sent from the probe, and the red circle is represent the eyeball. So for the first step, the probe is placed on one end of the eyeball. Second, an ultrasound wave is sent from the probe. At the same time, a line from the left of the screen will start to be drawn. It moves horizontally, measuring time. Next, as the wave reached the first wall of the eyeball, some of the ultrasound reflected back into the probe. It recorded on the line as a bump. The stronger the return wave, the higher the height of bump. The height of bump represents the amplitude. And then the ultrasound wave will continue further in the eye. Next, the wave then meets the end of the wall. Again, some of the ultrasound wave is reflected back into probe, resulting in another bump drawn. Next, the time difference between the first bump and the second bump represents how long the ultrasound wave took to travel between the two walls. So, if we know the time difference, which is the interval between the two bumps, we can calculate how far the wave traveled between the two walls of the eye, giving us the eyeball length.
In B mode scanning, unlike A mode, the strength of the wave is determined by the brightness of the dot instead of a bump. To make it easy to understand, let's use the eyeball as an example again, with a probe placed on one end. When the wave meets the first wall and reflected back, a bright dot is recorded. The wave continues and reaches the other wall, producing a bright dot on the screen just like the first one. And that is how BMOD scanning works. The thing is about BMOD scanning is that the images produced can be in two-dimensional. This is done when B-mode scan is made on different levels of the structure. To put it simply, the scan first starts on the top of the structure, and with the scan line of the first structure kept on the screen, it scans the lower structure and gradually scans the lower structures after that until it reaches the bottom. With this method, all levels of the structure is scanned, and scan line on the screen produce a 2D image of the structure. The process that happens is very quick and happens many times over a second. The complete description of this mode is real-time two-dimensional B-scan. The reason for two-dimensional is due to the fact that it has both x-axis and y-axis as shown in the image below. Finally, the examples of B-mode scanning can be seen in many things, including medical ultrasound. On the left is an image of a B-scan of the ventricle, and on the right is a scan of a fetus.
Next is probe selection. Introduction of probe selection. Probe selection can be described by the size and shape of their face, footprint. We need to select the right probe to get a good image. And then, there are three basic types of probe. First, linear, second, curvilinear, and third, phase array. So these are three types of probes. First, linear. Linear uses high-frequency ultrasound to create high-resolution image of structures near the body surface. It makes the probe ideal for vascular imaging and certain procedures such as central line placement. Next is curvilinear. Curvilinear uses lower frequency ultrasound, allowing a deep penetration and a wide depth of field. It is excellent for viewing intra-abdominal structures. Last but not least is phase array. Phase array probe give a large depth of field with a small footprint, allowing the ultrasound to view deep structures, though a small acoustic window. So, straight linear array probe. It designed for superficial imaging. The crystals are aligned in a linear fashion within a flat head. It also produces sound waves in a straight line. It has higher frequencies, which is 5 to 13 MHz, and it can provide better resolution and less penetration. The image produced is rectangular in shape, and it is ideal for imaging superficial structures. So these are the functions of linear probe: vascular access, evaluate for deep venous thrombosis, musculoskeletal, testicular, ocular ultrasounds, skin and soft tissue for abscess foreign body, appendicitis in teen patients, evaluation of the pleural line, and other procedures like arthrosynthesis, paracentesis, thoracentesis, and nerve blocks.
Next, we move to curvilinear array probe. The curvilinear array probe is used for scanning deeper structures. The crystals are aligned along a curved surface and cause a fanning out of the beam, which results in a field of view that is wider than the probe's footprint. This probe has frequency ranging between 1 to 8 MHz, which allows for greater penetration but less resolution. These probes are most often used in abdominal and pelvic application. This probe also can be used in procedures such as abdominal aorta, gallbladder, liver, pancreas, or transabdominal pelvic evaluation. The image generated by curvilinear array probe is sector shapes. For the example, this is abdominal ultrasound, which you can see the liver, kidney, and diaphragm. Next is endocavitary probe. The endocavitary probe is also has a curved face. It has higher frequency than the curvilinear probe, which is 8 to 13 MHz. This probe's elongated shape allows it to be inserted close to the anatomy being evaluated. This probe is used most commonly for gynecological application, which is transvaginal ultrasounds, or it also can be used for intraoral evaluation of peritonsillar abscesses, which is intraoral evaluation. The curved face creates a wide field of view of almost 118 degrees, and its high frequency provides superior resolution. This probe also produces a sector-shaped image but a much wider field of view. For the example, this is the transvaginal ultrasound imaging using the endocavitary probe, which you can see the bladder and the uterus. Last is the phase array probes. Phase array probes have crystals that are grouped closely together. The timing of the electrical pulse that are applied to the crystal varies, and they are fired in oscillating manner. The sound waves that are generated originate from a single point and fan outward, creating a sector type image. Parasternal long axis view image is produced by phase array probe when the probe points toward the right shoulder. As you can see in the image, you can see the right ventricle, aortic outflow, left ventricle, left atrium, and descending aorta. This probe has a smaller and flatter footprint than the curvilinear, which allow the user to maneuver more easily between the rib and small space. This probe have frequency between 2 and 8 MHz, but they usually operate at a higher end, making them ideal for echocardiography. The phase area probe can also function at lower frequency, which is useful for viewing the abdominal pelvic. This probe can be also used in procedures such as cardiac imaging, imaging between ribs in the flap, and also transabdominal imaging if curvilinear probe not available.